And we've got to the electricity homework booklet question 15, and we're shown a diagram of the battery, EMF 12 volts, internal resistance 1.5 ohms, connected to a 2 ohm resistor in parallel with an unknown resistor R, and the battery is supplying a current of 4.2 amps. Show the potential difference across the internal resistance is 6.3 volts. That's simply the PD across there, so we're just doing a V equals IR across there. That has got the full 4.2 amps going for it, so there's the mark, because it's a show question, is for doing an IR on that current and that internal PD. So the marks for that line there, that does get you to the 6.3 volts. We're asked to calculate the PD across the 2 ohm resistor. Well, the PD across here is going to be the same as across the 2 ohm resistor. It's going to be the same as across R, which is going to be the same as across the terminal PDs, which is the EMF take away the PD across the internal resistance that we've just worked out. In fact, just been told is 6.3. So it's 12 minus 6.3 is 5.7 volts. Single mark there. Got to calculate the current in it. Well, again, that's now just a V equals IR using that current we've been given. So I'm just using V equals IR on that particular resistor. I is V upon R. The 5.7 volts that's across that 2 ohm resistor divided by the 2 ohms of that resistor gets you to 2.85. It should round to 2.9. For some reason they accepted either 2.8 or 2.9. I think I'll tell you why they accepted either in a minute, in fact. And then we've got to determine the current in R. The point here is that we've got a current flowing into that point, and that's got to add up to the current flowing through there that we've just calculated, plus that. So these two currents, the current that's flowing through the 2 ohm, the current that's flowing through the unknown resistor, have to add up to the 4.2. You can see the same at this point, coming out of the 2 ohm, coming out of R, have to add up to the 4.2 that will be going our way around that section. So we've got the 4.2 amps in the main loop of the circuit, take off the current we've just worked out, and I get to 2.85. 1.35, which if you round it properly, or in the usual way, gives you to 1.4 amps. The only problem is if you round them both upwards, you get a total of 4.3, which is why they actually accepted either of them to have been rounded downwards. They accepted 1.3 or 1.4 there, because it would be tempting to round one up, one down, so they, after the rounding, they still add up to the 4.2 amps. Calculate the resistance of R. So very simple, just looking at R, doing V equals IR. R is V upon I. It was 5.7 across for 2 ohms. It's going to be the same across R because it's a parallel circuit. Divide that by the current we've just worked out going through R, and we get 4.2 ohms. Again, because of the ranges they've accepted before, they accepted 4.4 to 4.1. And then finally they ask you to, finally in part A, they ask you to calculate the total current of the circuit. So first of all, we've got the parallel combination of the 2 ohms and R, but we'll then have to add on, so we've got 2 ohms and R in parallel, we've worked out the value of R. We'll then have to add on that 1.5 if we want to talk about the total current in that circuit, total resistance in that circuit. So the calculation for the parallel is going to get us 1, and that gets us to 1.357. Need to add on the 1.5 for the internal resistance, 2.86, 2.9 ohms. We've got a battery converting chemical energy into electrical energy that's then dissipated by the internal resistor and the 2 external resistors. Using data values you've collected, complete the following table by calculating the rate of energy dissipated in each resistor. You can do it either way. You can either use P equals I squared R or P equals IV. So for the internal resistance, the current was 4.2, and the resistance 1.5, it turns out it's 26.5 watts. For the 2 ohm, we've got 2.85 amps going through, times R, 2 ohms, gives us 16.2, and for R, it's got that much current, 1.35. We had calculated a resistance of 4.2, which gets to 7.7 watts. You could also have done the first two using P equals IV, because in fact all three, I don't know why I've missed it off for R. Using power equals IV, we know the current flowing through the internal resistor, sorry, we know the PD across the internal resistor, and what have I got going on there? I've got the wrong values. I've written down the wrong values is what's going on there. But we do know the current going through the resistor, that should be 4.2, and V across the internal resistance we worked out previously, and we could do it for the 2 ohm and for R, in fact, in the same way. Those aren't the right values, but you can do it using P equals IV where you've got that data. Hence show the energy is conserved in the circuit. Well, we can add those values up to show the power dissipation in all the various resistors, and the total energy supplied is just IV for the EMF, so 12 times 4.2, that gives the energy supplied each second, is 50, again comes to the same value, therefore they're conserved. So we're simply adding those three numbers up and comparing it to IV for the EMF. So that's the electricity homework booklet question 15.